So welcome back. In this sequence, we will see that not only recursive type can be used to define list-like data structures, but in fact, they are general enough to define tree-like representation. And to understand that, we will come back on our example for databases. So the type for databases can be now the following subtypes. A database can be empty, and in which case it has no contact, or can be a node that has a contact in the node and a left child database and a right child database. So this is really a tree-like representation of a database, but we will also enforce an invariant in that data structure. The fact that if you have some data node with a child left, a contact C, and a right child right, it is well formed if every contact in left is lexicographically smaller than C, and every contact in right is lexicographically greater than C. So, for instance, this is an example of a representation of a database in the machine. What you get is a root with a data node containing the contact Luke. On the left, there is another data node that has no child but a contact named Leila. And on the right, you have another data node with no child but a contact named Yoda. And this value is indeed valid with respect to our invariant. So let us come back to our search function in the database. It is now a tree traversal defined by induction. So in the case where no contact is the database, it means that the database is empty, so we return an error. Otherwise, if the database is composed of a node, then there are several cases. If the contact on the node has the same name as the name you're looking for, then you have found the contact and you just have to return it. If the name you're looking for is smaller than the name of the contact of the node, then you have to go on the left. Otherwise, if the name is greater than the name of the contact on the node, you just have to go on the right. In the worst case, this function is unable to find the contact you're looking for. So it means that it has to traverse all the tree from the root to the leaves. So the number of nodes that we will cross along that path will be bounded by the height of the tree. In the opposite, the array-based implementation that we've done last week, we had to traverse the entire database. So it is unlikely that the height of the tree is equal to the number of contacts. Otherwise, this would mean that the tree is degenerated into a list. But in fact, it is actually possible to enforce the invariant that the tree is balanced and that the height is bound by the logarithm of the number of contacts. So this lookup function can be made logarithmic in the size of the database, which is very efficient comparing to a linear complexity search. So now let us come back to the insertion of a contact inside the database. Again, this function will be a tree traversal defined by recursion and by case analysis over the shape of the tree. If the tree has no contact, if the database is empty, then we just have to return a new database that only contains one node consisting of the contact with two empty children. If now the database is a node with some contact prime as a root, we first compare the name of this contact with the name of the contact we are trying to insert. If they are equal, then we have nothing to do. We can return the tree as is. If now the contact name is smaller than the contact on the node, then we know that we have to insert this contact on the left of the tree. And we can reuse the same tree on the right. So we have the same tree on the initial database and on the output database. Otherwise, if the contact name is greater than the contact on the root, then we have to insert the contact on the right, and again we are able to reuse the same subtree on the left than the one found in the input database. Graphically, we've got something like that. From an input database, a new database in which you have inserted a new node 8 has only new nodes for the path from the root to the new node. And a lot of subtrees here on the left subtrees can be reused from the input database. So comparing with the array-based implementation, this tree-like representation enables more sharing between the different versions of our database. So let's talk about removing an element of this tree-like representation for database. So imagine that we remove the root of this tree. Then we obtain two subtrees, and in the end we have to merge these two subtrees into one new tree, but it is a bit complicated. And we should be able to focus on this problem, which is a problem about tree, independently of the fact that it represents a database. And we will do so by applying a separation of concerns principle. So in order to implement this separation of concerns principle, we will have to use parameterized types that allow us to perform a modular development, and they will be presented in a future sequence.